started. Very happy to have Dipole Contreras here today. He's started his career in Waterloo at the university where he did his undergrad, and after that he went to UBC to Vancouver to work with Dr. Scott on the topics of cosmology, and today he's going to talk about parity and anisotropy measurements using various probes.
Okay, thank you. I've never been introduced before, so that was cool. Yeah, I'm originally from Toronto, so it's nice to be here and talk about science. So this talk is going to be split up into two parts. The first part is going to be concerning statistical anisotropy and something to do with CMB anomalies that you may have heard about, specifically dipole modulation. So just a crash course into the CMB. This plot here is what the temperature cosmic microwave background looks like as measured by Planck. If you remove things like foregrounds and you mask out the galaxy, these perturbations, these red and blue spots here are perturbations at the level of 1 in 10,000 or so, and they tell you a lot about what's happening in the universe. And these bottom plots are the polarization plots. So Q and the Stokes Q and U parameters. So Q is just what's the intensity here minus here, and then for U it's just rotated by 45 degrees. And because you have this extra degree of freedom, you can decompose the polarization into E modes and B modes, which share E modes share similar parity properties to the temperature, and B modes have opposite parity. So for most of cosmology, people talk about base Lambda CDM. So these are the 6 numbers that describe the large-scale universe really well. So to start, you need a description of what's causing the fluctuations. So the power spectrum is talked about in terms of a scale, A sub s, and N sub s tells you how the perturbations change depending on scale. And then you need to specify the things that are being fluctuated, so the baryons and the cold dark matter. And then you have some scale of the fluctuations, which tell you how far away the CMB is from us. And then, as always, there's a nuisance parameter we call tau, which is the optical depth to last scattering. It tells you after the universe became neutral, it reionized, and some of those photons from the CMB were scattered. And so we see a blurred CMB instead of the true CMB. So that's it's not a parameter like these other ones. If we knew all of astrophysics, we could tell you what tau was, but we don't. So it's a nuisance parameter. So if I give you these 6 numbers, then you can compute all the possible correlations in the CMB. So I'll show you those plots. This is the power spectrum that Planck produced. So just focus on the top one for now. This is the temperature power spectrum. And the first thing you'll notice, which is always kind of cool, that there's only 2,000 or so data points on here, whereas the original image I showed you had 10 million points. And that's just because you are only computing this 2-point statistic. And so most of the information is actually in 2,000 data points, not in the 10 million that I showed. The other thing you notice is the red line fits the data beautifully. So I didn't even need to tell you 2,000 numbers. I only need to tell you 6. And it fits the data wonderfully well. And then the other thing that's important here, the error bar is at the low L scale. So this L is on the x-axis. It's the harmonic scale. So at low L, these error bars have nothing to do with noise. They're simply what's called cosmic variance. So at low L, you're measuring the power on large patches of the sky. And because there's only a finite number of these size patches on the sky, and there's even less when I have a bigger patch. So that's why the error bar is so large on low L. And it's also conveniently where a lot of these CMB anomalies show up. It's at these large angular scales. The bottom plots are just the polarization power spectrum. So the one on the left is the temperature E mode polarization correlation. And then on the right is the E mode auto power spectrum. And conveniently, the L below 30 is not shown on here. And that's because there's residual systematics that were in the Planck data that they couldn't remove. So some of the data was not delivered, and that's gonna come up a little later. So part of the reason why I could reduce 10 million data points into 2,000 points on a power spectrum plot is because of these assumptions. So statistically isotropic, homogeneous, Gaussian universe. What that means in real space is that the correlation between any 2 points on the sky only depends on their distance and not their orientation. That's this first statement. In Fourier space, what that means is only K modes of the same magnitude and orientation are coupled. In multiple space, it means I can take the spherical harmonics and I only have to tell you the power, the CL of each. And you don't need to know that this part is cold and this part is hot. You just need to know what the statistics are. And then if I have Gaussianity, it just means I can write the likelihood of the data in this form. So just a simple Gaussian, where C is some covariance. So we don't want to assume that in this search because we want to look for a statistical anisotropy. So if I had statistical isotropy, then this covariance is diagonal in multiple space. So what I'm going to do is I'm just going to modify the covariance by adding a small anisotropic piece where X is some parameter that changes the CMB power spectrum. And if I run through this, if I input things that expand and I maximize the likelihood, then this bottom line here tells me how I can estimate what that anisotropic part is. And it's conveniently written in terms of the anisotropic part of the covariance and the isotropic part. So this is completely general. It could be used for any sort of anisotropic piece as long as it's linearly related in this way. So why would I want to do that? And the reason is this plot here. So this has been around for a while, since before WMAP even. And what I've done is I've shown the exact same data, except I filtered out some of the small scale stuff. So you notice the blobs here are bigger than normal. And I've centered the left side on the hemisphere that appears to have more power than the right side. So you'll notice, well, I don't know if you will notice, the plot on the left, the red and blue spots are redder and bluer than the ones on the right. So if you fit this, there's a dipole of the anisotropies on the sky, and this is a 6 to 7% dipole. Cosmic variance alone will give you a 2 or 3% dipole in these scales, so this is roughly a 3 sigma effect. So this, and these are on scales that are cosmic variance limited. So if I measure the sky again, I'm going to get the same answer. There's no noise here. This is real. This is how the universe is. So when people saw this, they introduced some sort of ansatz. They said, well, what if I just take my statistically isotropic sky and multiply by a dipole? That can explain this. And it can to some extent, except that we'll see that this signal doesn't go on to smaller scales. So just briefly, in the literature, this has been called many different things. So hemispheric asymmetry, power asymmetry, variance asymmetry. If you see any of these terms, they're all talking about the same thing. The effect is only 3 sigma, so with 3 sigma, I can't distinguish any of these things, even if they are intrinsically different. If I have a variance asymmetry, I'm going to have a power asymmetry. And there's been many attempts to explain this signal. Most of them do no better than cosmic variance. Well, actually, no, all of them do no better than cosmic variance. Okay, so if we go to, there's probably too much detail in this, but if I just say that I have some parameter, I try to explain this dipole modulation. So I have some parameter x, and it changes the power spectrum in some way, and I say this parameter has a gradient on the sky, so it has some mean value and then a dipole component. So it changes the ALMs, the temperature on the sky in this way. So there's the isotropic piece, and then the anisotropic piece is added on. And this forces coupling between modes, neighboring modes, so L and L+1. So the covariance that was diagonal now has off-diagonal pieces to it. And that's shown here. So the estimator, the same estimator I showed before, applied to dipole modulation looks like this. And this is a convenient form to express this, because the parameter, all you need to know is how the power spectrum changes when I change the parameter x. So I could put any parameter I want here. I could change the baryon content in a gradient across the sky. I could change the power across the sky, the helium abundance, you name it, and I could write it down this way. So the thing that people normally do is they talk about power. So they'll implicitly assume that the thing that modulated is this A sub s parameter, which just tells you how the scalar perturbations on the sky. So if I use this estimator to estimate the sky from the lowest L possible and scan to high L, I'll get this plot here. So on the left is a p-value for the dipole modulation. So it's essentially what is the size of the amplitude of the data compared to many simulations. So low p-values means it's very significant. Versus Lmax. So just for fun, can anyone tell me what feature they think is the most significant here? No. Okay. Well.
Are there errors in the plot?
Are there? There shouldn't be. So there shouldn't really be any noise here. Planck is not really. Noise doesn't come in here.
Well, then the lowest point would be
Right, the lowest point. So people like to point out this third dip here, even though, I mean, I really could have pointed out any of these dips if I wanted to. So this is this Lmax of 64 dip. That's where you get this 6 to 7% amplitude of dipole modulation.
Is it the blue curve we should looking at? Or?
So they should, in principle, all be the same. These are 4 different component separation methods the Planck uses, but it's all the same data.
So what about the dip at L of a couple hundred?
Over here? Yeah, so this is still roughly all the same data. If you compare the actual data, because it's comparing to their own set of simulations, but if you compare the data sets themselves, they're pretty much all on top of each other. But I mean, the difference between this and here isn't really significant.
What does this look like if you just take some random Gaussian realization of the sky?
Yeah, you get stuff like this a lot. So one of the things that you should realize is, I told you that the Lmax of 64 was 3 sigma, but that's because I told you it was Lmax 64. There's no reason why. Well, there's no a priori reason why to pick a specific scale and go with that, right? If I told you, the universe should be dipole modulated at Lmax of 100, and you go and look, and you say, well, no, it's not. The p-value is too big. But people single out 64. And the reason, I mean, I don't know exactly know why, but the connection to super Hubble physics is that 64 is roughly the scale of the horizon at last scattering. So if you thought you understood sub-horizon physics, then that's fine. But if you thought something special happened at larger scales, some pre-inflationary thing, or some inflationary thing happened, then that's roughly exactly where you would expect, anomalies to appear. So that's part of the motivation why to keep looking at this. The other thing, so if I didn't choose the Lmax and I just marginalized over it, then the significance of the whole thing becomes of order 10% or something. So it doesn't completely go away, but it definitely weakens the significance. And if we only had CMB temperature, this would be the end of the story, because there's no, like I said, everything here is pretty much cosmic variance limited. If I do the measurement with a better experiment, I'm going to get the exact same result. So the only way forward is to look for new modes. Look for something else that you can follow up this signal with. And that's what I'm trying to show here. So this is a pretty cool plot. I'm going to spend some time on it. So this axis here is us today. And then up here we have last scattering. So the green line is essentially the CMB, if you can see the green line here. And this blue, light blue, is Lmax of 64 roughly, and it coincides with the horizon scale at last scattering. So if I wanted to look for something else that could help me determine whether this dipole modulation signal was real, I want something close to last scattering, because if I had a gradient, then the amplitude would decrease as I move to things coming close to me. And I also want something that can access low k, or large scales. So for instance, ISW is an effect that only happens at low L. So it might be good, but you see it's sourced really close to us. And so you don't expect ISW to help. And indeed, it doesn't explain the signal. But if you had polarization, which is sourced in the same place that CMB temperature is, then you're in business. Another possibility is lensing, because you see lensing is sourced along the line of sight. So that you have all these scales. It goes quite high, and we'll talk about that in a bit. And then the other thing you might want to do, which isn't on this plot, is 21 centimeter. Some dark age is 21 centimeters, so redshifts of like 30 or 50, which would be up here. Okay, but in order to do that, you need some sort of formalism. So the signal I've been talking about exists in harmonic space, so in L. But in order to translate that into what you would see in these other probes, you need some sort of real space modulation. So we're going to assume that I can break up the perturbations on the sky into stuff that sources low L or low K modes and high K modes. And I'm just going to say, for some reason or other, the low K modes are dipole modulated with some gradient. And then I'm just going to enforce that the total power fits Lambda CDM power spectrum as it should. And then I'm going to parameterize the low L power in some way. So this is some function that goes from the Lambda CDM power to 0 smoothly. And there's just some transition. So Kc is some cutoff scale where lower than Kc, all these modes are modulated essentially. Higher than Kc, they're statistically isotropic. And then delta K is just some transition. It's just how smoothly do I transition from one to the other. So this should accommodate any sort of scale dependence that you thought the dipole modulation might have. Okay. So
but it doesn't really follow where structure it is. Just some transition, some nodes below some K value have a modulation, and above K value they don't. While what you see in your P value plot is something that's all over the place.
Right. So, I mean, the choice of this is you're trying to motivate with some idea that for some reason the low or the large scales are special, they're modular in some way. You don't really want to follow that curve too closely, otherwise you're in danger of doing very a posteriori things. You don't want to choose an estimator once you've already seen what the data. I mean, we've kind of done that, but if the idea is that the large scales are special in some way, then this is kind of an agnostic way of doing it. Okay, so to a good approximation, I can write down the temperature perturbations as the regular temperature perturbations at high L, and a modulated piece that only couples to low L. And so the covariance looks like the isotropic piece plus the anisotropic part, and C low refers to the power spectrum I would get if I put in the P low power spectrum from the temperature. So once I've done this, I know how the covariance looks like, and so I can write down a likelihood for the data, and I can fit the data, and I can use those parameters to look in other modes. So the first thing to do is to fit the temperature data. So this is what the temperature data looks like fit to it. So you'll notice that it's pretty bad. Nothing is constrained terribly well, or at all even.
What are the colors? Sure.
Yeah, so blue is 68%, and light blue is 95% contoured.
What is this weird one?
This one?
Yeah.
So it's 68 in here and then 95 out.
Oh, okay.
Yeah. So it's
Do you also fit other direction of the dipole?
Yes. I've implicitly marginalized over it. So there's a bigger plot with 5 columns, but yes. So this looks nothing like, there's clearly no strong detection here, but that's not very surprising, because I've taken a 3 sigma result and I've added 2 more parameters and fit to it. So 3 sigma shared amongst 2 more parameters, it's not going to look like anything. So we could have seen this coming, I guess. So what does this mean? So the best fit parameters for temperature look like this. So the red line is the power spectrum of the small scales that are modulated, and you'll see that it looks like it prefers the dip at 2 to 300 as opposed to the dip at 65 that I mentioned before, and with some amplitude of 2%. So this is roughly again some 3 sigma type amplitude. The green line is the actual anisotropic part. So it's essentially the red line multiplied by this 2%. So that's what the temperature data looks like. So if you want to, so now it's really easy to look at other modes, because you have this K-space formalism. You can just input the power spectrum into CAM. CAM is a thing that computes these power spectrum for you. So if you look at lensing, this is what so black is the regular lensing power spectrum. Red is the power spectrum of the low L modulated, and then the green is the actual anisotropic part multiplied by this by the amplitude. So if you had access to cosmic variance lensing, we don't, but let's say you did, the cosmic variance from that will give you an dipole modulation amplitude of roughly 2.7%. So at best, with lensing, you could hope for a 0.7 sigma detection, and that's even that's optimistic, because in principle, you would like to run this full parameter set with the lensing data. So lensing is a lost cause. It's not going to help us look for it's not going to help us determine whether this modulation is real or not. So you would hope that you could see it in polarization. So if you just focus on the green for a second. So the green is the EE polarization power spectrum. So and it's just a theory curve. There's no data on this plot. And the dashed green is what the best fit low L modulated power spectrum would be, given the best fit parameters from temperature. And then the blue is some estimate of the noise for Planck. So we don't really have a good estimate of the noise for Planck, but this is something. So the first thing you'll notice is the actual Planck data doesn't tell you anything over here. All these scales are filtered out. So you don't even if you had this, you don't even get to look at this bump. And then the other thing to notice is that noise is important everywhere on this curve. So you're far from cosmic variance limited in polarization. So it's going to be tough. We're working on it, but it's going to be tough to see if polarization can get you any further in determining whether the signal is real or not. The red line is the TE correlation, or the absolute value of the TE correlation, because it's a log plot. And the red dashed is, again, the piece that's modulated. And it's high here, but at the same time, there's more cosmic variance in the TE power spectrum, because you get the piece from temperature and the E modes. So it doesn't if you just had temperature and TE, it doesn't actually help that much. Okay, but let's say you're super ambitious and you look at the 21 centimeter power spectrum. So this is so after recombination, there's neutral universe, and then, there's neutral hydrogen in the universe, and there's a spin flip transition that hydrogen can undergo, and it emits a 21 centimeter photon. So there's in principle, there's a bath of 21 centimeter photons that we have access to, although there are no dark ages experiments yet. So the good thing is you basically have, at each redshift, you essentially have a full CMB that you can look at in some sense. You have some full 2D map at each redshift, so you have access to many more modes. In green, though, we have just some power spectrum of a single redshift, and then in green dashed is again the anisotropic piece. So the one thing you'll see is normally this should die out about 2 to 300, like it did in the other plots, but it's never relevant for this experiment, and that's simply because the 21 centimeter power is, at any given harmonic scale, it's dominated by high K modes. And that's because the matter power spectrum gets an extra K squared contribution due to the growth factor on those at that time. So you can't do much. But the good part about 21 centimeters is that you have all these shells, so you can perform these cross correlations. So if you want to look at the low L's, the low K contribution from low K, you can cross correlate between neighboring shells. So again, green is the regular cross correlation between two 21 centimeter shells, and green dashed is the anisotropic part. So you could see I can recover the contribution from low K. It's even more important than the total power spectrum. So in principle, we're working on this, but it seems like for cosmic variance limited, of course, with roughly 20 shells separated by the cutoff scale, you could recover something as significant as or as constraining as the temperature modes. So in principle, 21 centimeter, and I mean, so this is in the context of dipole modulation, but this is true regardless of dipole modulation. So if you're interested in stuff at low k, if there's this is more this is a general statement about that. So there's the fact that you have all these modes at different shells that you can cross correlate gives you access to many more scales than naively you might think.
So you said it can do as good as temperature. It can't do way better. It can just get about the same level.
Oh, yeah. So at some point, so this is kind of like the naive approach. I mean, you just imagine that there's these shells, and then you just keep cross-correlating them. At some point, if you add more shells in between, you're adding the same information, so you're not gaining too much. So in principle, you could do better if you had some more sophisticated tools. But in practice, that's you might do a little bit better, but you're roughly the same. But if you had temperature, polarization, and this, then you could certainly constrain the, if the signal really was there, you could either you could tell it apart from a fluke, or you could find that the universe really is dipole modulated on the large scales. So just to summarize part one, so we have this dipole modulation signal on the large scales of the CMB. The signal is not going away. This is a feature of the universe that is there, but it's not very significant. And cosmic variance does a fantastic job of explaining it, as do many models. So you'd like to look for independent modes, different ways of following up. So we have this formalism that lets us do that. And we've shown that the lensing, CMB lensing, can't help you out. And we're working on trying to figure out what Planck polarization will be able to do. So stay tuned for the 2016 Planck isotropy and statistics paper. And if you're super ambitious, we're also looking at 21 centimeter as an option for constraining this, or any sort of statistical anisotropy that could exist. Okay, so yeah.
So back on your p-value slide and when you're showing the database results, if you go out to high L max, shouldn't you see the motion-induced dipole?
Right. Yeah. So the fact that we're moving with respect to the CMB gives you a dipole modulation. So that dipole modulation is frequency dependent. So you will see it. You won't see it in the 2015 data because that's been removed. No, it's not been removed. Sorry, the simulations include that.
So assuming we know perfectly our direction,
right.
So you wouldn't have seen it even if you went to higher L max in those plots, for example.
Not in that analysis, but you can see it if you look. You can still see it. So there's the based on the 2013 data, there's a Planck paper that measured it, and the 2015 data also. There's a follow-up in the appendix of the isotropy and statistics paper that looks for that. So you will see it eventually, but the simulations included that piece. So on this particular analysis, you would not have seen it.
But it wouldn't just show up as the same kind of dipole modulation?
With some effective amplitude because of the frequency dependence. Yeah. Yeah. But yeah, you would have mistaken it as that. So I'm going to move on to part two unless there's any more questions.
So
yeah.
on the 21 centimeter thing, did you take velocity affects the redshift space distortion?
Yes, so that's the full, so the CAM 21 sources includes that piece as well. So that's it.
That's a 1 over k squared.
But the total contribution on those scales is not doesn't overcompensate. So yeah, I think. Okay, so part 2, I'm going to talk about parity violation constraints. Okay, so another introductory slide. So as I mentioned before, the information we have in the CMB comes in the form of temperature anisotropies. We have E mode and B mode polarization anisotropies. And if the universe is Gaussian and statistically isotropic, then all the information is from the 2-point correlations of all those fields that I mentioned. And further, if the universe respects parity transformations, or parity symmetry, then the correlation between TB and EB has to be 0. And I demonstrate that in this little picture. So the red octagon shaped is what the E mode polarization pattern looks like around a hotspot. So it's either parallel to hotspots or tangential, and B modes look like windmills. So if I run the CMB in a mirror, then the E modes look the same, but the B modes have flipped. So they pick up an extra sign. So if I correlate those two, this symmetry will guarantee that TB and EB have to have vanishing correlations. So what that means is I can use these correlations to look for parity violating signatures in the universe. So what kind of parity violations specifically? Well, we measure photons, so it makes sense to look in the photon sector. So if I have some coupling to FF dual, F is the Maxwell-Faraday tensor. So I can. These are all equivalent ways of writing that same Lagrangian interaction. And there's some motivations for why you might have this. So if this is the axion coupling, so if you had axions at some level, this coupling has to be there. You could also relate this to some sort of quintessence model. So if we focus on this way of writing it, if the time derivative of that pseudoscalar field is non-zero, then what happens is as photons propagate from the CMB towards us, the polarization will rotate on its way to us. And this is sometimes called cosmic birefringence, or rotation of the plane of polarization. Okay, so when people normally, or the first time I heard about birefringence, someone showed me this picture. So this is some crystal where the different polarization states of the photon will actually follow different optical paths. So you'll see this double image when really there's one version of the word there. So that's similar, but not quite what happens in this sort of interaction. So what you're doing is you're coupling to the different polarization states slightly differently, such that they get a phase difference, but the optical path remains the same. So these are two different interactions that would give me this rotation. The one on the left is if I had some sort of axion field or quintessence model, and this is what this does is it still gives you the weak equivalence principle, which just tells you that photons follow gravitational paths defined by the gravitational field. But it violates the Einstein equivalence principle, and that's because the polarization state is modified due to the presence of this extra field. So it's not parallelly transported the way it should be. Or I could have this sort of interaction. This is a Chern-Simons type term. So this p mu is just some fixed vector. If I just choose, some direction in space-time, has to be. So if I want this rotation, it has to be the time direction. Then I'm explicitly picking a space-time direction. So I violate Lorentz invariance, and for this measurement, these two models are indistinguishable. So I can't, if I found some sort of non-zero rotation, then I couldn't tell you, using this measurement, I couldn't tell you which scenario it's in. Oftentimes in the literature, you'll see some statement to the effect that a non-zero rotation has to imply this scenario, and it's not true, because I could be in the one on the left, which doesn't violate any, it doesn't give me Lorentz violation. Okay, so what's the actual observable here? So alpha is going to be the angle of rotation from the CMB towards us. And that's related to the time derivative of this field integrated along the line of sight. So this is how it modifies the CMB power spectrum. And in red, I've highlighted the TB and EB power spectrum. So these are normally 0 if alpha is 0, because then I don't have any parity violations. But in the presence of this field, then I will pick up, I will essentially rotate the E and B modes in such a way that I'll pick up these parity violating correlations. Unfortunately, this effect is completely degenerate with an uncertainty in the orientation of your polarization polarimeters. So if I gave you a detector, a polarimeter, and I told you that it's oriented like this, but it was really oriented like this, then everywhere that I'm mapping the sky, I would effectively rotate the polarization states, and so I would induce this exact effect. And so that's the main systematic of this whole of this effect, and it's going to turn out to be important. So in principle, I can look at the. If I wanted to measure this, I could easily just go ahead and take the TB and EB correlations and fit the predicted power spectrum to them and tell you what alpha was. Instead, I'm going to do something where I stack on the Q and U polarization states to pull out the the TB and EB correlations. So why would I do stacking? The main reason is that it's very easy. It's a completely map space-based approach, and so dealing with the mask is trivial. You just if there's a region where there's a mask, I just don't include that point in the statistics. The other reasons are, as I mentioned before, the polarization data of Planck was released with a whole bunch of red flags, and so one of them being is the noise properties of the data are not completely well understood. So with the process of stacking, you can minimize your sensitivity to the noise, or the impact of the noise, and so it's helpful for that reason. So I can take so essentially what I'm going to do is I'm going to take I'm going to locate all the temperature hotspots, or all the E mode hotspots. I'm going to take the Q and U in those locations, and then I'm going to perform this rotation and then stack all the Q and U on top of each other. And when I do that, I expect to get these relations. So the rotated Q stacked image is directly related to, if I'm stacking on temperature spots, it's directly related to the TE power spectrum, or if I'm stacking on E mode hotspots, it's directly related to the EE power spectrum. And for rotated U, I'm either sensitive to the TB power spectrum or the EB power spectrum. And these bias terms come in because it's a biased estimate of the power spectrum, since I'm only considering these hotspots and hot and cold spots. But you can estimate that from the data. Okay, so the other reason why you might want to do stacking is because it's pretty. So this is the exact same information that's in the TE correlation power spectrum and the EE correlation power spectrum. So you can decide for yourself whether you like to look at this or the other one. And these rings are exactly related to the peaks and troughs of the power spectrum themselves. So this is just, there's no magic here. It's just the map space version of the harmonic power spectrum that I showed before. So anything I can do in harmonic space, I can do in map space. So there's nothing new here. But the real things that constrain are these UR plots. So these are the same things, but the UR, which are sensitive to these TB and EB correlations. So you'll see they effectively look like noise, with the exception of this ugly pattern here, which is just an artifact of the pixelization scheme. Because you predict these azimuthally symmetric rings structures, this doesn't bias your results. It just adds to the scatter. So it's unclear whether I was supposed to show that or not, but it's there in the data and it doesn't really affect anything. So what you do with this is you fit, you have the prediction, you have the data, you can fit you can use the likelihood and fit the values for alpha. So when you explore the parameter space, you get these values. So you get roughly an angle of rotation of 0.3 degrees with some statistical uncertainty of 0.05, and then you do some null. If you do some null tests to null out the data, then you get something consistent with 0. So this looks, at first it looks like a strong detection of the rotation. So there's parity violation. Until you remember that systematic of not knowing how your detectors are oriented is completely degenerate with this signal. And so when you try to estimate what that is, you get something that's roughly 0.33 degrees as well.
How do you estimate that?
Sorry?
How do you estimate that?
So you effectively do some ground-based measurements on the detectors, and then
This is just what you know about the detectors.
this is just what you know about the detectors. Yeah. So there's some, and then there's some complicated modeling that you do to get that. So yeah, you have to know about your detectors to estimate that. Okay, so just to prove to you that there was actually signal in those plots, these are the angular profiles. So I've just averaged around these rings and picked out the features. So this is this should be analogous to the TB, and this should be close to the EB. So you can see, so the Lambda CDM prediction, or the no parity violation prediction, is just a straight line through 0 microkelvin. And you can see that that's not a horrible fit to the data, but the non-zero alpha is able to pick out these oscillatory features. So that's where you get this strong signal, and that's why you couldn't see it in the original stacks. And then this is just a plot of sort of the history of these measurements. So yeah, it's a bit bragging, I guess, but here's Planck, the latest Planck measurements. There's two data points here. The first one is the data with the statistical uncertainty, and then the second one is with the systematics added. So some of them, for instance, Bicep 2 didn't estimate their systematics uncertainty. So that's why there's only one data point there.
Over there and Bicep 2, I guess Bicep 2 doesn't have systematic support. polar bears have been detecting something. Is that what
I don't know about, yeah, that's like, yeah, half a segment or something. Yeah. There was for a while, people were really interested in the fact that all the CMB measurements were giving you negative alpha, even if they weren't super significant. I mean, I don't know.
Not anymore.
Yeah, not anymore. So we made progress. Okay, so I breezed over some of the. Actually, I'll just skip this slide. Actually. Okay, so how do we do better? We're systematics dominated. So one of the ways is you better control the systematics. I don't know how to do that. Smart detector people will have to do that. I mean, you would like there to be some strong polarized source in the sky that you could calibrate off of. So if you find one, let me know. But we don't. As far as I know, that's really hard to come by. Another way is again to look for new modes. So it would be cool if I could give you this same plot, but for polarization instead, and see what are the probes I should look at to see polarization at large distances. The other way forward, though, is to look at anisotropic birefringence. So this would be a scenario in which the angle of rotation depends on the direction of the sky. You would expect there to be anisotropic birefringence if the source of it was some field. So if it's some field, it has to be perturbed in some way. What the scale of that perturbation is, we don't quite know, but in principle, you would see this signal. So this is just a map of what alpha looks like on each sky. So here. I keep saying I, but this was actually we have a summer student helping us out. So she essentially just pixelized the sky and did the stacking on each of these pixels, estimated alpha, and then fit some sort of and well, she's going to fit what the alpha power spectrum will look like. But the 0.25 degrees is just the dipole part. So if you just fit a dipole, you'll get something of 0.25 degrees. Uncertainty is roughly 0.3 or 0.4 degrees. The current limits on a flat power spectrum of an alpha power spectrum are on the order of 1 degree squared. So that's the kind of.
So these are completely noise dominated, right?
Yeah. These are dominated by the statistical uncertainty. Yeah. So you don't get the systematics here because you're differencing. So the systematic will go away, but because you're looking at these patches, you don't have a lot of these things to stack on. So you'll introduce you'll have more statistical uncertainty. But this is work in progress. So there's stuff to be done. Okay, so just to summarize part 2, we've constrained this angle alpha in this way. It turns out to be consistent with no parity violation. So in the Planck paper, there's 2 approaches. There's this one that I talked about and the harmonic-based approach, which I mentioned earlier on. And they give completely consistent results. So we believe the results to be robust. So we're systematics dominated here. So it's hard to see where the future of this kind of measurement will go without some pretty strong advancements in calibrating your polarimeters. And we're looking at the anisotropic birefringence to maybe move further along. Okay, thanks.
Any questions? I had one, just your final remark regarding the anisotropy of birefringence. So, is this problematic if we do ground-based? Maybe someone else has the answer to this.
No, not really. So
Can't
the
be loud. Right?
no the
Because of course here you see the full sky, so if you talk about systematics, you're looking at one single experiment mapping out the whole sky systematically, but if you do ground-based, it's more of a patchwork. So maybe you introduce new systematics, maybe.
for the anisotropic part.
Right.
So the best limits come from the ground-based experiments because you have a deeper field of view. So you can.
Yeah, no, but in terms of anisotropy, you know what I mean?
Yeah. That's what I mean. So they do worse on the uniform rotation, but for the anisotropic part, you look for for high L specifically. Their constraints are the best because they have a stronger or a deeper.
But there, I mean, always the way you scan the sky, it doesn't introduce a systematics into this measurement, or no?
It can, but the statement is based just on where the noise is coming from, and since there's no sample variance here, you win by drilling very deep on it.
That I understand.
Yeah.
Because the planet is a relatively noisy measurement over the whole sky.
Right.
And on this as well.
But you would not measure Birefringence and anisotropy on large scales very well.
Oh, well, that's what they're doing. That's their
Yeah.
progress.
Yeah.
But he's saying the ground-based ones would be better. And
Even on large
systematics about the scanning, I don't know if anyone's thought that much about.
I don't know. I mean for the anisotropic part, I don't know that you. I don't think there's nothing as strong as the rotation piece for the uniform stuff. So I think you just measure. I mean, you have. It's a problem for lensing. It's essentially a lensing curl mode. Is how they do it in the ground-based ones. So the estimator is exactly the same as lensing, except you change the weights around because instead of displacing photons from their paths, you're just rotating slightly in different directions. So.
Okay. Any other questions? Okay, let's thank the again.